Thank you.
Thank you. And hello, everyone. My name is Fuchen from Tsinghua University, and I'm currently a postdoc researcher in Tsinghua. And here I'm glad to introduce you our recent work named Themis, which is a tool used to find the imbalance failures in distributed file systems through a load variance model. And this is a joint work with Harbin Institute of Technology too. And for the background part, in a distributed file system, we have several nodes or volumes that can be removed, replaced, or added. And there are so many files can be dynamically created, deleted, or appended. And all of these operations affect the load distribution in a distributed file system. And there are some load balancing mechanisms designed for distributed file system to ensure that the data and processing tasks are evenly distributed across all the nodes in the system. And this can prevent the overburdening and optimize the whole efficiency and throughput of the system. And however, the load balancing mechanisms are inherently complex, and there are some architectures to manage the data across multiple dynamically changing nodes. And consequently, it is difficult to avoid implementation errors in such mechanisms. So since the mechanisms are important for a distributed file system, and bugs in them may cause imbalance the load distribution, leading to some severe consequences, including the degraded performance such as throughput and latency, and potential service unavailability. And thereby, such failures may impact the whole reliability, availability, or the security of the distributed file systems. So to better understand the characteristics of the imbalance failures, we conducted historical imbalance bug studies on four popular distributed file systems, including the HDFS, SAFFS, GlusterFS, and LeoFS. And totally, we collected 53 imbalance failures in these systems, and we analyzed their root causes, their triggering conditions, and their consequences, and have some basic findings. And the first finding here is that we want to find out what the consequence these failures can cause. And we find that about 80% of the imbalance failures can lead to serious consequences that may affect all the distributed nodes or a majority of the distributed nodes, and that they will let the nodes degrade their throughput or their performance, or even they will let the node crash down. And our second finding, we want to find out the root cause of this imbalance failures, and we find that most imbalance failures are caused by the implementation errors in the data migration process of the load balancing mechanisms in the systems. Yeah, and our third finding, we want to find the symptoms of these imbalance failures, and we find that all the imbalance failures lead to significant disparities in the usage of computing resources, including the network traffic, the CPU, and the disk storage. And we then analyze the production steps for each imbalance failure to understand how these failures are triggered. And we find that most imbalance failures require both client workload requests and the system configuration changes to be triggered. And this is a two-dimension testing inputs for a testing tool. We not only need to generate some testing workloads to trigger the imbalance failures, we also need to change the configurations in the system. And for the next finding, we want to find out how these failures are triggered. And we find all the imbalance failures can be triggered with no more than 10 distributed nodes. And they just rapidly execute some short sequences with no more than 8 operations. And and can trigger the imbalance failures. And for the last founding, we recorded and analyzed the load changes during the imbalance failure triggering process, and we find that the ultimate load imbalance state in a DFS is usually caused by continuously accumulating many intermediate states of slight load variance. And based on these findings, we want to design a testing framework for the imbalance failures in distributed file systems. And here we select a motivating example to show how we did that and why existing tools fail. And here is an example of the imbalance bug in HDFS. And where in this bug, some incorrect data distribution calculation led to the service unavailability. And this bug is hidden in a deep path. To trigger this bug, there are at least 7 key steps should be executed. And the first is to add in some volume. And then we need operation like make director and create a fail and remove some volume and remove some data and remove some nodes. And then there is a new data operation. And after the 7 key steps, the bug can be triggered. For the details, you can refer to our paper to show how the bug is triggered. But with that example, we can see that to trigger such bugs, not only some workload requests should be generated, there are also some related to some system configuration settings. And existing work basically have 3 methods to test the whole distributed systems. And the first method to handle 2-dimension testing inputs is to just fix one input. And this is a straightforward approach to fix one type of input space and explore the other dimension. And however, this approach fails to explore the combinations of request and configuration inputs, and this can result in some ineffective detection of the imbalance failures bugs. And for the second method, we can alternately explore 2 dimensions of input by 3 steps. First, we can randomly generating a system configuration, and under that configuration setting, we can perform some testing process to explore the client request input space. And for the third step, if the exploration of the workload request input space is complete, we can generate another new random configuration setting and repeat the step 1 and step 2. And there are also the third method. And the third method is to concurrently generate 2 types of inputs, including the work requests and the system configurations. And this method struggles to effectively utilize some runtime feedback for the optimizing the input spaces. And since the request and the configuration inputs are generated concurrently and independently, it is challenging to identify which input type changes can trigger the current runtime status. And consequently, this method relies on a random search across the expensive input spaces, making it inefficient to detect such bugs. And here is our method. Unlike the existing tools, we present both changes to the system configuration and the user workload requests as a sequence of operations, instead of considering them as 2 independent input spaces. And based on this basic idea, we have our overall design of the tool named Themis. And we designed Themis as a test framework for imbalance failures bug finding in distributed file systems. And here is the basic workflow. It includes the two main components. The first one is a test case generator for generating high-quality test cases. And the second one is an imbalance bug detector for identifying if some imbalance failures occur. And first, Themis first constructs a test case input model that describes both client requests and system configurations. And based on the model, Themis converts both request and configuration inputs into an operation sequence named OPSEC. And from figure, we can see that OP-sec contains several operations, OP1, OP2, and OPN. And each operation can both represent a workload request or system configuration settings. And after that, we will generate some test cases based on the OP-sec. And the first generated test cases, we called it the initial test cases. We will store it into a seed pool for the further testing and seed selection. And based on a load variance model, Themis can generate new test cases by selecting and mutating the existing seeds from the seed pool. And here is the load variance model designed in the Themis. And the model contains 4 parts. And the first part is the computation load data. And this data indicates the core computation distribution of each node, including the number of CPU cores and the utilization of each CPU core. And the second part is a network load data. And this includes the I/O usage information and for both reading and writing part. And the second part is the storage load data. And this represents the average size of data stored in each node during the system runtime. And last part, we have a load variance calculation method to calculate the extent of the variance extent of each node currently in the running system. And based on the load variance model, we generate each test cases for each testing round, and then we use the DFS to execute such operating sequences. And then we use the imbalance detector to monitor and collect the runtime load data. This includes the CPU usage, storage distribution for each node from the distributed file system. And the load variance between distributed nodes is calculated in the real time and to judge whether some bugs occur. And the load variance model is updated accordingly based on the calculation results from the load variance model. And meanwhile, imbalance detector identifies the imbalance states and reports the imbalance failures once they are detected. And according to our finding, the imbalance detector is designed to monitor the runtime load status of nodes in the DFS and identify any unreasonable load imbalance. Specifically, if the maximum load among the nodes exceeds the average node load, and we have a threshold T to judge whether the current load variance is considering as a bug. And if the variance calculated results is bigger than T, the threshold, then we think a bug occurs. And based on Themis, we currently find 10 imbalance bugs in 4 distributed file systems, including HDFS and CFFS. And we also compared our method with the state-of-the-art methods for 2-dimension input generation testing, including fixed one-input generation testing and concurrently generating 2-dimension in testing inputs. And the results show that our tool Themis can always outperform others on 4 targets distributed file systems. And to evaluate the effectiveness of the load variance model, we also implement another version of Themis named the Themis minus. And this is a version that disables the load variance model and generates operation sequence randomly. And in conclusion, Themis can detect all 10 bugs within 24 hours, while Themis minus only detect 5 of them. And we find Themis can cover 11% more code coverage than Themis minus. And to evaluate the impact of the variance threshold value T on the accuracy and false positives, we conducted experiments running Themis with various T value setups. And we find that a higher threshold value effectively reduced the false positives. And based on our experimental results, we find a threshold T of 25% represents an optimal balance. eliminating all the false positives across the 4 target DFSs without missing any true positives. And our future work mainly focuses on two points. The first one is we want to detect more bug types in distributed file systems, like file slow bugs and metadata inconsistency. And for this part, we have just got a paper accepted by Uselink Security 25 to detect metadata inconsistency bugs in distributed file systems. And for the second part of our future work, we want to improve and fix the citing for the threshold T, because this may influence the false positive rate. And we want to dynamically adjust the threshold and use some machine learning technology to set the threshold more properly. And that's all. Thank you for listening. And please contact us if you have any further questions. Thank you.